Assalamu alaikum. Welcome to today's session. So, in the last class, we were discussing about the dynamic modeling for a flyball type governor system. Specifically, we were looking at different scenarios associated with the operation of the flyball type governor. So we actually took examples of probably 3 different scenarios out of 4 that I targeted to discuss. So scenario number 1, what we actually did, we took the example of the scenario. We took the example where the case was linked with the load change at the shaft. And based on that, there will be some speed deviation detected at this point of the system. And accordingly, there will be change in the distance between the fly balls. Point B will be shifted downwards. Point C will be shifted downwards. D will be shifted downwards. And correspondingly, there will be some openings in the lower side, this side. And the high pressure oil is there, so it will flow through this channel opening, the next slide that was shown. And accordingly, the force will be there, which will push this beak shaft into the upwards direction. So this was scenario number 1. Okay, so accordingly, we completed this. So this was the continuation of the scenario 1, actually. So this was the starting of scenario 1, and this was the completion of scenario 1, where the system settles back at the desired speed or the reference speed. And at this point, at this scenario, point A was kept unchanged. So we are not actually touching the reference set point for the speed changer. Then scenario 1 was the reverse case of scenario. Scenario 2 was the reverse case for scenario 1. So in this case, at the initial part, again, the speed was sensed, but now the load at the generator was decreased. So because of the load decrement, the mechanical power input was higher at the beginning, and accordingly generator accelerated. And because of that, the speed increased momentarily. And again, set point was kept fixed. That means point A was kept fixed. It was untouched. So the speed was sensed, and because there was higher speed, so the fly ball distance is increased. The spring stretched a little bit. Point B, C, and D, they all came down, and accordingly, there was the opening at the lower chamber, and it felt the pressure from the bottom end. And we saw that this beak shaft, this opening of the channel for the steam flow to the turbine was getting closed, okay, or getting smaller. So actually, probably I started from not the correct slide. So this was starting of the scenario 1. Actually, this thing happened. Okay, so at the starting of the scenario 1, the upper chamber was actually opened, and then in the completion part, the channel got closed. Okay, so there's a correction a little bit. And then this is scenario 2, and again at the completion of scenario 2, again both of these channels here, upper channel and lower channel, both of them will be again closed. So system will settle down to a steady state speed, but of course with a lower opening. Why the lower opening is required? Because the load has been decreased, so we actually need to supply less electrical output from the generator. So because the load is decreased, in this case load got decreased at the beginning, the starting phase of scenario 2. So we need to reduce PE. We don't want to supply additional PE, okay, which is not required actually. So we don't have to produce additional PE, and PE is coming due to PM. So we have to reduce PM, and accordingly this channel was getting smaller. So a smaller amount of steam was flowing to the turbine blades. So less amount of mechanical input was available. So this was scenario 2. In both cases, scenario 1 and 2, A was unchanged. Point A was unchanged. Then we went on to scenario 3. Now we are not changing the load anymore. So what we did actually, we put point A into the downwards direction. Okay, we pull it down. So as soon as we pull it down and we are not changing the load at the beginning or at the starting phase of scenario 3, so PL is unchanged. PL is unchanged. So initially omega is unchanged. Initially omega is unchanged because still PM equals to PE. This condition is still satisfied. But so to start with, what we are doing, we are changing point A position. So as soon as we change position A, speed is fixed here. So there is no deviation in speed being sensed by the sensing mechanism or by the sensor. So the fly ball distance kept fixed. The spring distance remained fixed. Point B remained fixed. But because of point B being the pivot point here for the part ABC or the arm ABC, this arm. So A was going down, or we pulled it down actually. We are setting it to a different speed set point. Speed set point. So as we said in the first of the diagram, if we lower point A, what do we expect? So when we lower point A, so if this point is lowered, actually we expect a rise in the mechanical input. Okay, rise in the ultimately we will expect a rise in the mechanical input or rise in the steam input. So that is expected. Let's see whether we get it or not at the end of scenario number 3. So the speed set point, or in other words, the PM set point, we are changing it. We are pulling it down. We are pulling this down. So ultimately we expect this. So if A goes down, we expect PM to go up. So this is the relationship. So we started from point A, and then once we pull it down, and again we set it fixed at the new point. So probably before shifting, point A was here, somewhere here. And now after we shift it, it goes down a little bit. Okay, so this was the initial point. So we can call it A initial, and this is our A new. But now again, A new has been fixed, and we are looking at the operation of the other part of the mechanism. Okay, A new again is fixed to a new position. So as A goes, so this is scenario 3 actually. So let's go to scenario 4. This is scenario 3, slide 2. Yeah, okay. Scenario 3, slide 1. So this is scenario 3 starting. So because of point B being the pivot point, it will remain fixed. It's not going to be changed. Point B is the pivot point. So on the other end, as A is getting down, C will go up. As C goes down, it pulls point D also along with it. So point D also gets a force in the upwards direction along with C. And accordingly, because D is connected directly to this piston valve, so this piston valve gets a force in the upwards direction. So as it moves up, the upper channel here, the upper channel gets opened, and accordingly, you get a force from the high pressure oil on the heavy piston or main piston in the downwards direction. So what will happen? This heavy piston will move down, and it will take point E along with it. So point E moves down. So D is moving up, but E is moving down. So what will happen ultimately? This channel will have a greater opening, a larger opening. Ultimately, what will happen? Your steam input will increase, and as soon as your steam input increases, the turbine here will get more input. So you are in a position now to provide more mechanical input to the system. Okay. So as more mechanical input is available, but you haven't, let's say you haven't increased the load yet. Okay, you haven't increased the load yet. You simply changed the position of point A. So what will happen? there will be acceleration. So PM is now higher than the required PE. So that means you are now in a position to increase the demand actually. Okay, you can increase the demand and then you can again settle down the speed. So now you are in a position by changing point A to this A new, which is actually lower than A initial in this case. So you are in a position to increase PM, and that would make you, that will enable you to increase the PE or supply more electric demand, electrical output by the generator. So this was scenario number 3. Now let's move on to scenario number 4, which would be, of course, just the opposite case of scenario number 3. So again, in scenario 4, what will happen? We will have a starting phase. So in the starting phase, again, we are not going to change the load. Okay. So PE remains fixed, P load or PL remains fixed. And then let's see what happens. So this is scenario 3 finishing. Okay, so scenario 4. So again, what we do here, we are changing point A now in the reverse direction. So point A moves up. So this is, let's say this was probably A initial, and this is our A new now. So we are moving in the upwards direction. So A new is greater than A in. Okay. And accordingly, if we change A, it has a close impact or direct connection with the change in PM. So if we raise point A, then PM is supposed to be decreased. So this is our expectation. So let's see how it is achieved by this mechanism. So point A is raised initially. So because the speed, remember, PL is fixed. PE would be fixed. So, and still there is nothing has yet happened at this point. Okay, nothing has happened to the steam flow. So it's still at this point PM is fixed. Okay, PA would be affected ultimately, but not right now. Okay, it will not happen instantaneously. It will take some time. The time constant will be associated there. So PM is still fixed to its initial value. Just we have changed the position of point A for the time being. So PM minus PE is still 0. So there is no acceleration. So speed is fixed. So shaft fly ball distance will be fixed. Shaft speed will be fixed. Point B is fixed. But because again, point B is the pivot point for this part, A, B, C here. So as soon as A goes up, so C should come down. So as C comes down, it also pulls point D along with itself. So point D also comes down. As D comes down, this piston, the piston valve, the smaller piston, it comes down from its previous position. So there is an opening in the lower chamber or lower channel, and this will be the force. So due to this force, this heavy piston will move up, and it will also pull point E into the upwards direction. So as soon as point E goes up, this channel gets closed, or smaller actually, to be precise. This channel becomes smaller. There is less steam flow available to the turbine blades. So ultimately, if this happens, so this must happen. So if steam flow is decreasing, PM is decreasing. So this is what will actually happen. Now as PM is decreasing, so PM got decreased. So there will be a negative PM minus PE, negative PM minus PE, and there will be retardation or deceleration. So the shaft speed will slow down a little bit, okay? Depending on this magnitude of difference, of course. So the shaft speed will slow down. Now, as soon as the shaft speed slows down, what will happen? That we will show in the next slide. So let's finish it here. So point C comes down, as I have shown here. Point D also comes down. Piston valve here comes down, and the high pressure oil passes through the lower opening. It's about this. Point E goes up. So point E is going up, main valve goes up. This is the main valve, it is going up. And the steam input falls. Okay, steam input reduces or decreases. Okay, so now we have a reduction in the speed. So that reduction in speed, why reduction in speed? Because PM is getting reduced, PE is still there because we haven't touched the load. Okay, load is fixed to the initial value, but PM has got reduced. So that because of that, we have a negative value and there is a negative acceleration. So speed, the outcome of all these will be the speed gets decreased. So that speed change will be, of course, sensed by this mechanism that we will show in the next slide. So point A, now we are not touching point A. So once we have fixed point A to the new position, we are not touching it anymore. So point A is still unmoved. Shaft speed decreased. So as we said in the previous slide, at the ending part, the shaft speed will be decreased. So once the shaft speed gets decreased, that will be sensed by the speed sensing mechanism. And accordingly, what we will get. So again, let's start from here. So the shaft speed gets decreased, that is sensed over here. If the shaft speed gets decreased due to the spring pressure, okay, due to the spring tension, the fly balls will be pulled inside, okay, pulled closer to each other. The spring will get compressed due to the tension. And point B will get a pressure or get a force into the upwards direction due to this movement of the fly balls and the compression of the spring at the same time. So point B goes up. So it will, now point A is fixed. Remember, point E is fixed. So as B goes up, B is the pivot point. So it will pull point C along with itself. So B and C both will move up. As C moves up, it will also pull point D along with itself. So D also moves up. As D moves up, you compare it with the previous diagram. In the previous diagram for scenario 4, you see the chamber. This chamber was open, lower chamber. Okay, so now if point D goes up in the next slide, what will happen? Slowly, this channel will be closed because this piston valve will be moving up. So as it moves up, slowly this channel will be closed. So that is shown actually in the next slide. So you see now this channel, there is no opening. Okay, no opening is left there. And as it goes up, there is no further high pressure oil moving through these in either of these channels. Okay, so there is no further pressure on this heavy piston being created by this high pressure oil. So point E doesn't move anymore. Okay, so point E doesn't move anymore. So the piston valve goes up, channel gets closed. Both of these channels gets closed actually. So the lower channel was opened. So now it will become closed due to the upper movement of D into the upwards direction. Point E is unmoved because there is no other pressure. Okay, no pressure is there. No pressure is there. And the main valve, because point E is unmoved, as the same time this main piston will also remain unmoved. No change. Steam input remains unchanged. Steam input remains unchanged. Okay. So what we have got actually, we have got a new PM value actually. So we have got a new PM value, PM new now is of course less than PM initial. Okay, PM new is now less than PM initial. We have a continuous now speed, you see it is a decreased speed. It is a decreased speed. It is not the synchronous speed. From with respect to the steady state, initial steady state value of PM in, there we had omega synchronous, but now speed is reduced and it is continuing in that manner. So you have to bring back the speed to synchronous. What we have to do, we have to reduce some load because you don't have enough PM in or PM actually. So you have to now, to make the balance, to keep the balance again, to establish the balance between PM and PE, what we have to do, we have to reduce PE. That means we have to shed some load. This is of course because all these are happening because we are simply changing this reference point. Okay. Okay, any question up to now? No question. Okay, so this is the physical mechanism. Now let's let's become a little bit more mathematical and try to get the required dynamics for this mechanism. Okay, so now let's look into the modeling part. So what we will do, we will assume some pretty simple things to start with. So what we say to start with, let's say point A. So now because we have the background, can anyone say what is happening with point A here? If we change point A, what are we achieving? If we change point A, upwards or downwards direction, what can we achieve? Anyone? And similarly, if point E is changed, what can we achieve?
So we are changing the set point.
Yes. By changing point A, we can have a change in P command, we can say. Okay. In the book, they are saying it in terms of commanded P command. Okay. It's all the same as P ref. You can say P mechanical reference or P reference set point. So if point A goes up, what happens to the commanded power? The power commanded or power reference set point actually decreases. If we reduce point A, then PC or P command, which is the same actually as P ref, we can also say it P ref, that will go up. That is happening here. Okay. So that control is actually lying with point A movement. What is happening with point E? If point E is getting moved up or down, what can we achieve?
PM.
Yeah. So this is actually Pref. We can change the Pref reference set point or commanded value. We can command it. And this is directly controlling PM. So if point E goes up, what is happening to PM?
Decreasing.
Yes, PM is getting decreased because this channel is getting closed. And if E goes down, so this channel is getting wider. So PM goes up. So we can have a close relation between point E with PM and point A with the reference power. So that is actually being said in the first few lines here. So let's say we take the distance of point A and point E from a fixed horizontal reference. So that means we can say, let's say that is the initial steady state equilibrium point. So with respect to the steady state operating point, what we are saying that point A is related with a power change setting. Okay, that is PC or P command. And point E, it is basically they are calling it the valve power. Okay, because ultimately it will go and become, ultimately it will provide us PM, but I mean, evidently, I mean, we cannot say directly from here that that is PM. Rather, what they are saying is simply it is the valve power available. PSV, steam valve. Okay, because we are talking about some steam governor mechanism. So they are calling it valve power or PSV. Okay, simply it means the closing and opening of this valve. Okay, if you have more opening, then steam valve, if PSV is more, means E has to be getting downwards. If you expect PSV to be less, E has to be moved up. That's it. So specifically at this point, at this very point, they are calling it PSV. Okay, not PM. PM will be available ultimately once the turbine rotates. So PSV is actually coming here, and PM is the output of turbine. Okay. If you neglect the losses, of course, you can call like PSV is PM, something like that, or some conversion will be there. Unit conversion probably will be required. Okay. But they are related, very closely related. PM, that is the mechanical, the output of turbine, and the mechanical input to the generator that will ultimately go to the generator shaft. And PSV is actually at this point. So this is PSV point, the steam valve power. So now, if we have any incremental change in the positions of points A, B, and C. So we're talking about 3 points which are linked with a single arm, A, B, and C, where point B is the pivot. So B is the center point. Depending on which this point A and C might move. Okay, so this is the pivot point. So A, B, C are related by this relation. That means if you have any incremental change in point B, Y is nothing but the change in position. Okay, change in height, you can say. Y is nothing but change in position. So change in the position is represented by the letter Y, small y. Delta means, okay, the change. Y is the position, delta is the change in the position, and B is the specific point. It can be A, B, C, D, E. We have 5 points. So you can have A, B, C, D, and E. So this is the explanation of delta YB. So delta YB is related with what? It is related with del YA and del YC. And KBA and KBC are nothing but some proportionality constant. Okay. In other words, what we are simply saying that if there is any change in A, or if there is any change in C, point C, both of them could be related with the change in point B. So that means they can be related by some proportionality constant, and this KBA and KBC are nothing but the proportionality constant. Because B is the center point, so you are saying that KBA, so B is involved in both cases, BA and BC. So when we're looking at the relation between the change in position of point B and change in position in point A, we are bringing the proportionality constant KB and A. Okay, so we are writing this proportionality constant like B and A. When we are talking about point B and point C relation and changing relation between their changes in position, so we call it like B and C. So this is as simple as that. And we have already seen that how actually they are related, okay? How they are actually affecting each other's position. Now, can anyone tell me how is the change in A is affecting the change in B? Again, I repeat the question. How is the change in A, I mean physically, how it is affecting the change in B? Which scenario explains this part? Forget about this for the time being, because they are 2 different points. So how can we write this? Is it okay? There's some comment. No problem. The child is sleeping, so okay, you are excused. Anyone? Ashif, are you there?
Yes, sir.
Okay, can you respond? How can we relate this? Because we are talking many things, but we have to be familiar with what is going on here. Small things. Then we can establish the bigger picture. So in the smaller picture, the question is how we are relating the movement in point A with the movement in point B. Is it a logical relation? It seems very straightforward, but
The
physically.
speed is changing. Speed is changing, so we are writing the proportionality constant.
When point A changes, what happens? Position of point A changes. What will happen? Let's see. If point A changes, let's say in the downwards direction, okay? The command is raise. The PC gets a command that raise your value. That means ultimately that command will be satisfied by PSV, okay, here. So there is an initial command raise. So we have to, that means we are actually bringing point A downwards. So if A goes down, remember, initially there is no change in shaft speed with the change in the position of A. So that means initially there is no change in point B. That's why I'm asking the question. There is no direct relation of A and B, at least at the beginning phase. Ultimately, B gets affected. So as A goes down, shaft speed remains fixed. C goes up. Remember, C goes up. If C goes up, D also goes up. If D goes up, which channel gets opened? The upper channel gets opened. So point E goes down. Okay, there is more steam input. So PSV increases. That increases PM. If PM increases, PE remains fixed. PM minus PE becomes positive. I'm giving you simply the flashback of what I just mentioned in the previous part of today's lecture. PM minus PE gets positive. If this gets positive, there is acceleration. Omega increases. That increase in omega is sensed here. If omega increases, these fly balls gets apart. Okay, goes apart. Point B goes down. So this is how you see now the relationship. This is how they are related. After so many steps, they get affected by each other. Is it clear?
Yes, sir.
Okay, so this is how it gets affected. Similarly, we can find this relationship. Okay. Similarly, you can find this relationship. Okay. It is pretty straightforward. If A remains fixed, now forget about this. If A remains fixed, then if B moves upwards, C of course will move upwards. If B goes down, C goes down, and vice versa. So that is pretty straightforward, but this one is not that straightforward. So that's why I just explained all these steps. And that is related to scenario 3 or 4 actually, where we actually changed the position of point A from our side. That means we changed the commanded power. Okay. So similarly, because point D is another pivot point, and that is linked with the arm CDE. So in the same manner, we can write a similar relationship for those 3 points there, C, D, and E. They would be related like in the similar manner. Now the position of B and D will be just changed. So instead of B, we write the next pivot point for this arm, CDE. So now this is the next arm where this is the pivot point. So this is the pivot point change in pivot point position. Then you see D and C. So D comes from here and C comes from there, and DE. These are again proportionality constants, DC and DE. Okay. So now if we want to relate point A with the commanded power, the commanded power was represented by PC. So now if there is any change in point A, any change in the position of point A, that is again proportional to the commanded power, PC. So del YA should be equals to proportional to del PC, or del PC proportional to del YA, and we simply bring a proportionality constant KA just to establish the equation from the proportionality relationship. So that is del PC and del YA relationship. Now what we do next? Well, there are some, of course, dynamics of the fly ball and the spring, okay? because we said that the fly ball is getting apart, okay, getting away from each other, going away from each other when the spring is stretched. The fly balls comes closer when the spring gets compressed. So there is a dynamics, of course, associated with the fly ball position change. But for the simplicity of our derivation, we are neglecting it because that is not our main target. Our main target is actually associated with the dynamics, what is happening here. Okay, we are actually focusing on the dynamics here, not in the dynamics here. So of course, there are some dynamics. You can try and capture that dynamics through the modeling, but that is ignored for simplicity of the model. So we neglect the fly ball dynamics. And remember, the fly ball dynamics actually affects the point B position. Okay, the fly ball dynamics affects the point B position, because as soon as the fly ball position changes, the point B actually either lowers itself or raises itself. Whereas that is being neglected or ignored. Now we focus simply on some steady state relationship. So as soon as there is some speed being sensed here, difference in speed being sensed or change in speed being sensed, that change in speed can be denoted by delta omega. That is the actual rotor speed. And this is related to the change in position B. Okay, this is related to the change in position of point B. So they are proportional. That means the point B will change as soon as any shaft speed deviation is being detected. So they are proportional. If shaft speed increases, point B goes down. If shaft speed decreases, point B goes up. So in this case, in this derivation, actually, any movement in the downwards direction is treated as positive. Remember, any point movement or position movement of any of the points towards the downwards direction is treated as positive movement, whereas any point movement in the upwards direction is treated as a negative movement. Okay, please keep it in mind, because you see, if we move point A, we are getting some raised positive change in the command del PC. So del PC becomes positive. So we said del YA. Remember in the previous slide, we said del YA is proportional to del PC, or vice versa. Sorry, the vice versa. Del PC is proportional to del YA. So, but we are lowering point A, right? We are lowering point A, but we are writing it as positive change because of our convention that we are adopting here. So any change in the downwards direction is treated as positive. Okay. So that's why this is okay. There's no problem with this. So any change in point B, if a speed increase is sensed, shaft speed increase is sensed. So that means a positive change in del omega, positive del YB. Why positive? Because if the shaft speed increases, these 2 points will move apart from each other and point B will go down, and that downwards movement is positive. So that's why del YB is positive. So del omega is proportional to actually del YB. And just to make it a speed value, we are multiplying it by the omega base. Okay. So del omega is proportional to omega base KB into del YB. Okay. Now, so what we have done, we have got the idea of point A change, that is this commanded power, point B change, that is the speed deviation. Point C is actually not connected with any other part of the mechanism directly. It is not controlling any other directly. It is not like point B is controlled or controlling the fly ball position. Point A is controlling the PC change. Point D is controlling the piston valve directly. Point E is controlling the main valve position. So point C, unlike others, it is not actually directly changing anything. So points, you don't see del yc equal to something else. Okay, but you will see del ya, you have already seen. You will see del yb, you have already seen. You will see del yd and del ye, but not del yc. There is no other part associated with it directly. So now we move on to point D. So now point D and point E has a very interesting relation in between them. Okay, point D and point E has a very interesting relationship between them. So if point D, that means the piston valve position, if point D moves down, what will happen? Sorry, if point D moves down, that will give us a del yd positive. Okay, that will give us a del yd positive. So if point D moves down, what happens to point E? If point D moves down, the lower channel will be opened, right? This channel will be opened if this whole thing moves downwards. And the heavy piston, the main piston, will get a force through the high pressure oil into the upwards direction. So what will happen to the point E movement? It will move up. So always point D and point E, they have an opposite relationship. Okay, with respect to sign, they have an opposite relationship. So if point D goes down, point E will go up. So positive del yd means actually negative del ye. But if we are interested in the dynamics of this, then we have to take this d by dt with it. So basically this movement, point D movement and point E movement, is not instantaneous. That means once the point D moves, then the oil has to flow in and oil has to put the pressure on the main piston valve, which is a pretty heavy part of the mechanism. So it will take some time. So it will not be an instantaneous thing like this. Okay, it will not be a steady state or algebraic relationship. Rather, it will be a dynamic relationship because of the time associated with the change or time required with the change. So instead of writing it simply like del yd is minus del ye, we have to take into account the d by dt term. So the change in position, in the position of point A, the dynamics of that with respect to time is proportional to minus del yt. Okay, because they have an opposite relationship and because we are actually trying to capture the dynamics associated with the valve movement here. So that's why we are putting this d by dt term. Okay, and when we remove the proportionality constant, simply we introduce this proportion. When we remove the proportionality sign here, we have to introduce this proportionality constant ke here. So that is d by dt del ye equals to minus ke del yt. Okay, so then now we are almost done because we have taken all the possible relationships available for del ya, for del yb, for del yd and del ye. Now we will replace them in the first two equations of our derivation. So the first two equations was simply this two, del yb equals to this. So now what we will do, actually slowly we will be replacing the expressions of del ya. Del ya will be replaced by this, or could be replaced by this. So del ya has a corresponding other expression. Del yc has nothing. Okay, del yc, we haven't done anything with del yc. We didn't get any other relationship for del yc, but del ya we have a relationship. Similarly for del yd and del ye, we have got some relationship. So let's see how we are going to replace them one by one. So first what we do, we replace del yd in the above equation directly. So what is del yd? Del yd, remember, is the second equation, this equation. So simply instead of del yd, what we will do, we will write this in terms of del yc and del ye. So this is your del yd replaced by second equation of our derivation, kdc del yc plus kde del ye. So d del ye by dt equals to minus ke kdc del yc plus kde del ye. Next, what we do, so now we replace del yc. So what is del yc? Now del yc can be written, of course, in terms of del yb and del ya. Okay, so del yc can be replaced like this from the first equation. So this is what we have done. So del yc. So what we have, you see, kdc del yc plus kde del ye, and overall that is multiplied with ke. So we are interested in replacing this del yc with the help of the second equation. So we won't see any del yc. Instead of that, we will see something del yd, kdc, kde, and del ye. So this is what we have, kdc and del yb minus kba del ya by kbc. Okay, so well, we can do it in both ways. We can use this expression for replacing del yc, or we can also use this expression. All the same, some different proportionality constant will come. So probably here they are simply using this. So instead of del yc, they are using del yb and del ya and kba and kbc, not this one. So that is done. So that means this del yc is taken from equation 1, not equation 2. Okay, there's a correction. This is from equation 1 in terms of del yb and del ya, and the remaining things remains as it is in this equation, the last equation. So still on the left hand side, we have the dynamics of point A, or deviation in point A position, minus ke kdc. This is the update of del yc, and this was already there, kde del ye. Now we replace del ya and del yb. So del ya is what? Del ya is, okay, so after replacing, there are some actually manipulations. So after that manipulation is done, so you won't see any del ya. Instead of del ya, what you would see? You would see del ya is where? So del ya is del pc over ka. So del yc is del pc over ka. So you see del pc over ka is there. So that means this del ya is no more there. And again, there is some multiplication and some simplification, okay, nothing else. So you see minus ke kde del ye is there. This is the last part, and these two are actually splitted. So the first one is getting a minus sign. So del yb is what? Del yb is taken from the expression present over here. So del yb should be del omega divided by omega base kb. So that is taken here, del omega base kb. So this is your actually del yb replacement, and kdc by kbc ke. So this is there, ke kdc, sorry, kbc kdc by kbc, and minus sign is there. Then this minus and this minus becomes plus, and you take the remaining thing. Pretty straightforward. Okay, so this simplification, nothing else. Okay, so once the simplification, and we rewrite this equation in terms of this equation, and now we have another proportionality relation that is between PSV and del YE. Okay, and that is a little complicated like this. So del YE and PSV, they are related in this way. They are proportional, of course, but the proportionality constant is like this, kdc kba over kd kbc ka. So then we define a new term, that is droop. Can anyone tell what is droop for a governor or for a synchronous generator governor? What is droop? No one?
Sir, droop ki damping tai droop.
Not the damping droop. Simply droop means it is something like something dropping, okay? Something dropping down, moving downwards through a slope. So droop means actually this. Let's say if you are, I mean, just moving a little bit away from this topic actually. Let's say if I want to mention that, let's say you have a motor. Okay, this is a motor. This is the shaft. And there is a mechanical load. So the motor, let's say it is a DC motor, simply DC motor. So you are providing some, of course, input, electrical input, so that there is a torque and there is a corresponding speed omega 1, and let's say that is around 1500 rpm. So initially there is no load. Okay, so no load at the shaft of the motor. Simply you are connecting, providing the electrical input to the motor, and you are getting something speed around 1500 rpm. So at no mechanical load being put at the shaft, so this is, let's say, the load. So at zero load, this is, let's say, the speed. Your speed is 1500 rpm. Okay. Now, if we increase the load, let's say 10 kilogram load is being put at the on the shaft of the motor, DC motor. What do you expect with the speed? You are not changing anything from the input side. You are not controlling anything. So now what is expected?
The speed reduce.
Speed will reduce. Excellent. If you so this is 10 kg, this is 20, let's say this is 50. So what would be the trend of speed change? It will be dropping, right? It will be dropping until and unless you are changing, let's say, the voltage input, or you are doing something to control the speed, to bring the speed back to its no load speed. Okay, for doing that, you have to change some parameter at the input side. You have to control some of the parameters of the motor, but we are not, let's say, we are not doing anything. We are simply keeping on increasing the load at the shaft of the motor, and we are simply observing the speed deviation. So with this increase in load, you see the speed or the frequency of rotation of the motor is actually dropping down, right? From some reference value, from some no load value. This is omega no load. This is omega no load, and this is omega actual. So with this change in load, the speed is dropping, or the frequency is dropping, frequency of rotation actually for the motor. This characteristics, you may call it as drooping characteristics. Now in terms of generator, what is the case? In terms of generator, again, if you are not providing any change, any control at the generator input side through the mechanical input, actually, you are not changing any mechanical input to the system. If you, let's say, if that is PM minus PE, that is, again, always we are going back to the simple equation, PM minus PE, 1 upon twice H, this is d omega by dt, right? This is the swing equation in per unit. Now, if the load demand increases for this generator here, if the load demand increases, generator, what it will try to do? It will try to supply the demand. Demand means it will try to supply more current, I load, at a constant voltage. Okay, let's say the voltage is constant. We are trying to keep it constant by the excitation system. So voltage is constant, but the load demand is increasing. Generator would try to provide more current to the load, but we are not controlling the PM. So with respect to a steady state operating point, okay, with respect to steady state operating point, if PE is increasing than PM, what would happen to d omega by dt? Let's say before the load increased, it was 50 megawatt and 50 megawatt. So d omega by dt would be 0 before the load was increased. Okay, now the load has increased. to 70 megawatt. So like the motor, okay, we are increasing the load demand. It is 70 megawatt. What would happen to d omega by dt?
Sir, reduce.
It will reduce. So the speed, until and unless we are putting more steam, if it's a steam turbine, steam generation system, steam generator scheme. So if we are not providing any further input through the PM, then actually this speed will slowly fall down. The rotor speed will fall like this. So if we require more power, P load, your speed of the rotor is expected to fall down continuously as you are increasing the demand. Okay, so this drop in speed with the change in required power to be supplied by the system is the droop. And this characteristics in drop in speed with the change in load demand is known as the droop characteristics. Okay, this is the droop characteristics. Okay. So that droop is actually defined here by some mathematical relationship, nothing else. So that droop is here, it is defined as kBA into kB by Ka omega base by twice pi, and this is the time constant associated with our dynamics. The time constant is defined as 1 upon Ke into KDE. So with these two definitions, and with the introduction of this proportionality between the change in the position of point E and change in the steam valve power, we will rewrite this, okay, this equation. We'll try to simplify this, nothing else. We'll try to simplify this with these new notations. So we will see probably droop. The term droop will arrive in the next slide. The term TSV will arrive in the next slide. And this proportionality will have some impact there. So in the next slide, what we do, we simply look at this. Okay, clear this. So what we do, you see, we have the presence of TSV here. Okay, so as I said, this is the steam valve time constant, steam valve mechanism or steam turbine mechanism time constant. Okay, so TSV d del PSV by dt. So simply what we are doing, we are actually playing with this. So you see del YE is actually some function of del PSV. So what we are doing, we are keeping the del PSV only here. We are replacing del YE by the whole thing. And we are keeping the del PSV there, and the remaining things are, remember, all these are proportionality constants. So we are taking them all to the other side and multiplying with this whole thing here. So this del YE is replaced by this whole thing. Del YE is replaced by this whole thing. The del YE, these constants, whatever proportionality constants are coming on this side, on the left hand side after replacement, are taken to the other side, and there will be some cancellation, of course. There are many terms, there will be some cancellations. Droop, we will be replacing droop by some terms here. So you say, so you can see KBA, KB over KA. KB over KA omega base by twice pi. So we will see it there. TSV is 1 by KE, KDE. So all these are incorporated actually in this single expression. So if you do the simple, calculation, I hope you will get, you can reach here pretty easily. Okay, so this is the model that we are looking for, and that is known as the incremental governor model. Incremental governor model for a steam turbine. Why incremental? Because you see the presence of del, d del, okay, that is a small change or incremental change in the steam valve position or steam valve power. You can call it position, you can call it power, they're all the same because the position and power are actually interlinked. Steam valve position is actually controlling the steam valve power. This del PC is the command power or power commanded with the help of the movement of point A. And omega base is the base angular speed, that is 2 pi f. And this droop, this term droop is actually nothing but the droop we defined here. So there is another definition of droop, actually, alternate definition of droop, and the notation of droop will be in that case RD, and RD is defined as twice pi droop by omega base. But this is just simply an alternate representation. So that will actually, of course, change this expression a little bit. Simply, this RD is inverse, simply taken as inverse of this. You can clearly see that RD is actually 1 upon whatever thing is appearing here within this bracket. So we can write this whole thing as 1 upon RD, where RD, this is RD twice pi droop by omega base. And here, before that, the unit for droop is actually hertz per unit megawatt. So this droop is actually hertz per unit megawatt. Okay, because you see there will be some hertz, omega base by twice pi, so there will be some f base will be there, so that will give you the hertz, and this proportionality constant, they will actually combine and ultimately give you some unit in terms of per unit megawatt. Okay, per unit megawatt. Okay, so now if instead of looking for the incremental model, if we are interested in an equilibrium point, okay, or in other words, for any incremental model, we are actually always build the incremental model with respect to a certain equilibrium point. Okay, so initially, before the disturbance or before the increment in the variable, we assume that we were operating at some certain equilibrium point or a steady state operating point. And from the steady state operating point, what we do is simply have a small deviation, and we look at the dynamics. We look at the disturbance response for the dynamics. So this is the corresponding equilibrium point for which this incremental governor model will be valid, will remain valid. Of course, this is a generalized expression. But if we put any specific value of PC, PSV, omega naught, then for that specific value, this specific incremental governor model will be valid. If we change the operating point, probably some of the values has to be updated. Okay. So probably there is, so for operation near an equilibrium point, we have PC naught equal to PSV naught 1 upon RD omega naught by omega base minus 1. So how is this coming? Simply for an equilibrium point, what you have to do, simply you have to take this part equals to 0, because for a steady state operation, there is no dynamics, there is no d by dt. So simply you have to take it equals to 0, and simply you have to change the sides and make this one equals to 1 upon RD. That will, and then if you simplify this, probably you will get this result. So this is for the specific operating point. Okay, specific operating point. Now, this is the equilibrium point expression. This is the incremental model for the actual per unit values, or the actual or the representation of the governor model in terms of the actual parameters or actual variables. By actual, I mean it is not the incremental variable, it is not the equilibrium point expression, it is the actual value. So simply what we are saying that this is with respect to some, d del x by dt. This is in terms of x naught, and this is in terms of x, where x is equal to del x plus x0. So this is the, we can say, non-linear variable. You can also say non-linear variable. This is the linearized variable. This is the initial operating point. So this is the actual representation of the variables. PC is equal to del PC plus PC naught. PSV equals to del PSV plus PSV naught, and so on. Now the governor dynamics, ultimately, this is the steam governor, of course, in terms of the actual variables, where all the variables are in per unit. This is TSV. Now we simply get rid of this delta term, this delta term, this delta term, and this delta term. So if we get rid of all those, then simply we reach here. Now, because that is a non-linear expression, so there will be some associated limits. Because why this limit is to be implemented or is to be expressed like this, because you see the steam valve position or steam valve power. Steam valve can have a maximum, it can provide a maximum power. What is the maximum power position? Let's go and see the picture. For the maximum power position, you see it can maximum probably come up to this point. So once, so to increase the steam flow or steam valve position or steam flow input to the turbine, this has to come down. Okay. So if this comes down, ultimately probably at this point, it will get stuck. So it cannot go beyond this point. So there is a maximum opening possible. There is a maximum possible opening for the steam valve. On the other hand, on the reverse side, this if steam input has to be reduced, then this main valve has to be moved up, and probably when it comes here, then there is no further opening. So that is 0. So thus there are limits associated with this steam valve power or steam valve position, PSV, and they are translated as this. 0 is the minimum value of PSV, and there is a maximum value of PSV. There is, of course, no minus value. Remember, there is no minus steam valve position. It can get a 0 value with 0 steam input, and it can provide us a maximum steam input with the position set at PSV max. Now, because this line is actually, I have written here, just to make us comfortable with the earlier derivations that we did for hydro turbine. Remember, in the hydro turbine case, the power flow to the hydro turbine was actually governed by the gate valve position. If you remember, the gate valve position, and that gate valve position was denoted by G, if you remember. Okay. And before we started this part of discussion of governor modeling, we were actually in a problem. Let's go back to the problem and try to finish it here. So in the hydro turbine modeling part, at the end, we found some equations like this, where we had two differential variables. So in the left hand side, we had the mechanical torque as a differential in the differential form, d by dt of Tm. However, we also had the gate valve position G, of course, in per unit, but that was also present there in terms of d by dt. And this gate valve position was actually controlling the hydro flow or the water flow to the hydro turbine. So what we said at the beginning of the governor modeling, we said that we want to get rid of this term. And if you remember, I said that we want to get this expression, remove this expression with the help of some equivalent algebraic expression. So this is the gate valve for hydro turbine, but the derivation here we did up to this point, it was the steam valve position or steam valve power, PSV. If we simply try to mimic the whole governor mechanism for a hydro turbine, we have to replace this time constant of a steam turbine by the governor time constant for hydro turbine, that is TG. PSV, it is for steam turbine, that is the steam valve position or steam valve power. The corresponding gate valve position for hydro turbine will be G. So simply you see we are getting some form dG over dt. Again, PSV is the steam valve position or steam valve power. G is the gate valve position for hydro turbine. PC is the commanded power. It is okay, it's fine, no problem. RD is the corresponding droop. It is also fine. Omega by omega base. Omega is the original or actual speed of the rotor. Omega base is the base speed. -1 is the constant. And similar to PSV, that is the steam valve position or steam valve power, we have a gate valve maximum point, of course, and a 0 gate valve position. That means when the gate valve is fully closed, it is 0. And when the gate valve is fully opened, it is actually 1 or G max. So now you can see that if we try to mimic this governor operation for the hydro turbine with the operation of the steam turbine, simply we can replace some of the parameters and we get an expression of dG over dt on the right hand side, which is an algebraic expression. So if we replace these thing, of course, there will be some 1 by Tg multiplied with the whole thing. 1 by Tg, if I take Tg here on the right hand side. So it will become 1 by Tg multiplied by the whole thing. And then this thing we have to replace in slide number 10 here. Actually, this Tg will become Tw. So Tw and Tg are same, water turbine time constant. Okay, Tw here and Tg there actually are same. So you can also write it at, just to remove any ambiguity, simply write it as Tw. Okay, that's it. So that means you have Tw dg by dt available here now, and we simply replace it with this part, which is in algebraic form, luckily. So Tw dg by dt can be replaced by the expression we derived today, and accordingly we can see that we have found a complete state space model now. So in our state space model, what we have now, we have, let us write it here. We have one expression like d delta by dt. This is our first expression. D omega by dt. This is the second expression. D eq prime. Of course, there is some delta because this is in incremental form. D del eq prime by dt. That is the internal qx is internal voltage. D del efd by dt. That is the exciter dynamics. D del tm by dt. That is the mechanical torque coming from the hydro turbine, and the governor d del g by dt. So this is the complete model if we incorporate the exciter, the hydro turbine, and the hydro governor. So the first three are associated with the generator. Fourth one is the exciter, and this is turbine, and this is governor. So this is more or less a simplified model for your dynamic study of a power system, having incorporated after we incorporate the exciter dynamics, the turbine dynamics, and the governor dynamics. However, much more complex models are available. Even for the generator, you can have probably a 6th order model. If we include the dx is, that is ed dash, you can include it. And you can, this is in the transient period. You can also include the sub-transient period. So if we include the two other, you will get something like this. So in total, probably a 6th order model is the maximum or the highest order model that you can go for. But in this course, we are simply interested in up to the 3rd order model, but you can go up to the 6th order model. That will be probably 3.3. Model 3.3. But in this course, we are taking probably 2.1. Okay, so then exciter, again, exciter, we took a very simple model ultimately, but as we know, there are the amplifier or the voltage regulator dynamics is there. So there are a few more equations that could be incorporated here. And again, the fly ball dynamics is ignored here. You can include the fly ball dynamics. Probably there also we did some simplification. So all these models are pretty simplified model still, okay? But you can go for much more complex model depending on your necessity, okay? Depending on your necessity of study and the complexity required for capturing any specific phenomena happening throughout your power system, okay? So that's it for the time being for the machine model and the governor model and the turbine model and the exciter model. Next, in the next class, inshallah, what we will start with the load model, okay? So the next class, we will go to the load model. So see you then, inshallah. Any question?
Assalamu alaikum, sir.
Walaikum assalam. Yeah, any question? We are simply saying goodbye. Okay, so probably this salam is for goodbye. Okay. Okay, say goodbye then. Okay. Assalamu alaikum.